All right, this is section 16.7a, surface integrals. Obviously, there's going to be a B. Part A, we'll do the basic idea of what's going on with the surface integrals, and we'll be able to find surface integrals of scalar functions. And then in 16.7b, it's going to get a little bit more involved. The videos will be a little bit longer. Let's start off with a general idea of what we're talking about, though. Now, so we've talked about already the idea of parameterizing a surface in order to be able to do this. So what we're looking at maybe now is, and this is probably the best idea that I can give, if we take the example, and by the way, I completely stole this from somebody else, a good friend of mine who does this, so I'm using his example. I think it's a really good one. If we were to kind of sketch 1/8 of the world, 1/8 of the globe, so you're talking about basically 1/8 of a sphere. So maybe, comes around here like this, and then goes up like this, and then like that. And remember, all we're talking about is the outside. We are not talking about, the mantle and the crust and the core of the globe or the earth or whatever. We're just talking about what's going on the surface. So the idea is this. Let's see how well I can do this geographically. If I were to, let's go with yellow here. If I were to sketch something in the northern hemisphere, like where we're at right now, maybe you've got, let's see, what would be like Greenland up here. Greenland's pretty big overall, something like that. And then Canada starts here, comes down, then we get towards the United States, hit Maine, to New York, Maryland somewhere in there, down here to Florida. That's really big, but you get the idea. Here's Florida, and then we've got the big Gulf of Mexico, and then it goes down into Mexico or something like that. Just trying to give somewhat of a geometric representation here. And then on this side, Mexico comes up, goes out towards California. It's kind of flat over here. California up into Canada. Alaska starts up in here somewhere. And then, of course, up here you've got your polar ice cap, the Arctic area, and so on. And then out on the side here, we've got, this is the ocean out here. This is the Atlantic Ocean out in this area right here. Didn't know you were getting a geographic lesson here, huh? Over here is the Pacific. I didn't go too far out in the Pacific on the left-hand side there. And then, of course, up here on the top, while it is ice, I'm going to go ahead and put that it's water up here still because it's still like frozen. But that's your oceans. You've got a little bit of places on the inside here where you've got your Great Lakes and stuff like that. I'll just put those as like the Great Lakes. The idea is this. If we want to figure out what the population density is of this 1/8 of the globe, this specific 1/8 of the Earth, what we need to kind of define the population densities at a whole bunch of different places. Well, everything in blue, there's basically no population. I mean, there's a little bit. You've got islands, out there, and you've got a couple little places, but other than that, there's pretty much nothing. So for the blue section here, in blue, we're basically going to say that there's none. There's very little. I mean, you got Bermuda out there and, a couple little islands and stuff like that. But for the most part, there's no population density there. And then you've got places like in northern Canada. Let's go with like purple for that or something. So you got places up here in like northern Canada, which is way up here. Greenland, which is very, very sparsely populated. Northern Canada, not much population. Not too much out here in Alaska, a little bit. Not too much, though. You got these places which are really sparsely populated. So you're just going to have maybe a few people per mile. So we'll just say a few people per square mile or per mile. And then you've got This section, we'll do this in red. Canada, it's populated, not extremely populated in a lot of parts, but it is populated. So we've got some population up here. The middle of the United States, especially in the mountain time zone, not extremely populated. Some of the Midwest countries, states and things like that, not extremely populated. A little bit of places in the south, not too bad overall. And then maybe, I don't know, maybe some places down here in Mexico that aren't extremely populated, something like that. Anyway, so you've got your red. We're going to call the red a moderate population. Populated, just not extremely populated. And then, of course, you've got your coasts of the United States, your East Coast, your West Coast, where most of the population is. You definitely have some places in the southern part of the United States, Texas, and Mexico City, stuff like that. Those are extremely populated, so we'll put those in green. So that's very high population density. Anything along the coast is usually quite populated, very popular areas there. Couple little places up here in Canada like Toronto and stuff like that have a very large population. And again, Texas, a Houston area, very, very populated down here, New Orleans, stuff like that. And again, a little bit of places, especially on the coast of Mexico, you got a high population. So we're going to call that a very dense population. And so the goal is, if I were to take all of this information, everything in here, the goal is to use the map that we've created to approximate the population of the number of people per square mile on this 1/8 of the Earth. That's the goal. Okay, and remember, this is only on the surface. We're not talking about the inside of the Earth. People don't generally live under the Earth, not into the mantle and the crust and stuff like that. You're not going to find that. So we're just talking about the surface integral of this whole thing. That's the general idea. Well, what we're going to be given is some kind of a scalar function. Some kind of a scalar function here, which represents a very small portion of the population. Maybe we're going to be able to take, this little patch right here, I don't know, someplace out here towards like, the tip of Florida or something like that. Probably not the best example, but maybe that's where it is. So we'll take that place right there, and maybe that's where we're going to try and find this scalar function. So, it'll be given to us as some kind of function of x and y, or similarly, it could be a function in the fact that it's spherical in phi and theta. And whatever that's going to give us. So, let me scroll up here. So maybe if we're looking at this thing in terms of, let me just try and redraw it real quick, but without all the colors on there. Maybe we're going to take and we're going to separate this into a whole bunch of different latitudes and longitudes, which kind of patches this thing up for us. And we said, someplace around Florida. So I said maybe someplace like out in here, somewhere in there. Maybe it's actually off the coast of Florida or something. Who knows? And we're going to look at this specific patch right here. And we're going to use that dot, that green dot in there, to approximate the entire patch. Well, maybe it's going to be some kind of a function, because this is spherical. Maybe it's going to be f of, I don't know, what does that look like? Maybe we went around this way. It looks like maybe pi thirds came down. Maybe pi thirds or so. So pi thirds maybe for phi and theta. And maybe we say that there is approximately 0.2 people per square mile. Just making this up at this point because I have no idea what it would be there, but maybe it's 0.2 people per square mile. And maybe what we're given here is that each one of these patches is like a, we'll say that the patch, whoops, it's supposed to be red. Try that again. We'll say that the patch is maybe like a, I don't know, a 90 by 100 mile or square mile area. So we know that the area of our patch, area of that one particular patch is, what's that, 900 times 100 is 90, no, 90,000? No. Oh, I'm sorry. That should not be a 900. That's way too big of a patch. That should be 90. There we go. Yeah, that's going to make it a lot easier to figure this out. Okay, so the area of our patch is 90 by 100, which is about 90,000. So 90, oops, can't write with an eraser. 90 times 100, which is a 9,000 square miles area. So if I want to find the actual amount of people per that one patch, I'm going to take the amount of people per square mile, which is 0.2, multiply that by my total area, and we're going to get the number of people for that one patch, or an approximation for the number of people for that one patch. So in this case, if I took the 9,000 and I multiplied that by 0.2, multiplying it by 2 is 18,000, so move the 1,800. So we're approximating that there would be about 1,800 people in that one patch. And the idea is then if I can create those patches and make those patches really, really super small, then I can actually get a really strong approximation for the area, for the population density. So what I want to do is I want to take and I want to sum all the patches. I want to sum all the patches as theta goes from 0 to pi halves, but then I want to take all the sums that I get from theta going from 0 to pi halves, and I want to add up all of those columns, or I guess longitudes maybe, I don't know, in the phi direction, so then I'm going to add up all those. So we're going to end up doing a double integral. So we're going to write the double integral, and our double integral now is an integral over the surface area. It's not over a d in this case, it's over the surface area of whatever the function of phi and theta is. But then I have to multiply that by the area of the surface, or the ds. But really, if I take the integral, the double integral of the surface area of f of phi and theta, if you recall from last time, the area of one of those patches could be written as the magnitude of the cross product of the partial derivatives. And then it would be over a dA. So this portion right here, let's see if I can illustrate this. This ds is that. That whole thing right there is ds, but this piece by itself was just the area of the patch, assuming it is parameterized. That's a very big key. It has to be parameterized in order for us to do this like this.